So this is actually a less, well, it was intended as a less technical talk. Maybe it's actually too technical. So this is more of a story about a history of Dutch of data systems development in the Netherlands. I am an old hand, so I started studying computer science in 1988, and I graduated in 1992. And at that moment, there was hardly a kind of systems or IT ecosystem. Well, there was no ecosystem in IT in the Netherlands. So all the software at that moment came from California, from Silicon Valley. A place that you, of course, aspired maybe to work at that time. But yeah, if you did not want to move to the United States, there was not so much to do in IT. Of course, there was a lot of IT work, but like being a consultant and implementing software that had been developed in the United States, in Europe. So that was for a long time the reality. And well, I chose in the end to go into research. So yeah, now I'm a professor and a group leader and researcher for a long time. So I did not become a consultant, but I did find it at that moment very frustrating that that you had to go to the United States in order to do kind of the high end of like development, and creating database systems is high end because it's a quite involved sport. Okay, so but yeah, there is a long history. I've been in this place for a long time, as you now hear, for like 30 years. And a lot has happened. And the situation is now different in Amsterdam and in the Netherlands. So we have got Databricks, ClickHouse with relatively large groups here, and also medium-sized companies like DuckDB Labs and ModderDuck and Polars. Elasticsearch is not a medium-sized company, but they are huge, of course, but they are medium-sized in the Netherlands. But they started in the Netherlands, actually, Elasticsearch. So, and that means, I mean, that this ecosystem that we completely did not have in the Netherlands when I was graduating as a young computer scientist, it's maybe starting to shape up. Now, in an ecosystem, you need more than just a couple of companies. What you need is people, a lot of people like you in the room, who have skills and who will also migrate from company to company. So now you may be thinking, oh, but maybe I shall talk to the Databricks recruiter or to the ClickHouse recruiter. And for companies, Amsterdam becomes also a more logical place, or the Netherlands becomes a more logical place to have an office, because there are people who you could hire. Okay, and that was not the case 30 years ago. And I, as a professor, but as a professor also educating, so we teach courses to students, and many of my students now work in the data systems industry. Some of them are in the room, quite a few are in the room. So it's a bit terraforming. You need to create like business. An ecosystem consists of kind of business. It consists of people with skills. There's a social aspect to it, and there are also still aspects that we are very much missing, like a financial ecosystem, like people specializing in, for instance, startups and VCs. Okay, they exist in the Netherlands, but let's say if you compare the ecosystems between US and the Netherlands, it's still, and Europe in general, it's still a long way off. But things have improved. I mean, they improved from nothing, essentially. Oh, by the way, here there's one of the other things that we do, but well, we try, of course, to educate at universities by giving courses, but and doing PhD education and raising new generations of data systems researchers. But we also do things like organizing conferences. Like in 2019, we had the biggest academic database conference called SIGMOD in Amsterdam. I say it's academic, but SIGMOD also has a lot of companies. All the big companies are there, and all the more like technical research people, they visit these conferences. And every other year now we organize CIDR, which is the conference on innovative database research. It is now organized 1 year in California and 1 year in Amsterdam. It's also a way to, I think, cross-pollinate and get people, well, to know that Amsterdam is a data systems place. VCs come there as well. Okay. Anyway, so that was a bit my intro of my intro, now the real intro. So I was already saying, yeah, data systems engineering. So actually making database systems, not necessarily using them, but the innards of it. That is one of the most complex tasks in computer science. People would say nowadays it's machine learning or devising a new model. I don't think so. Machine learning is tinkering with some parameters and throwing a lot of money and compute cycles at the pile, but making database systems costs really 5 to 10 years. You cannot do it in 1 year. You need a team of people. It's always an investment of millions of euros, even if it's open source. It's the practical cost of it's the time of people that you should definitely value at that amount of money, and also the source code and the project that you develop in whatever language you develop your database system. It's very large, and it's actually larger than operating systems. So database systems tend to be the biggest piece of source code that exists, or the biggest repositories. It's very difficult to comprehend. Maybe in very large and mature systems, there might not be a single person in a company that actually knows the complete source code of, for instance, Oracle, because it's so huge. And it comes all together here: compression, data structures, algorithms, optimization, machine learning now, compiler techniques, operating system techniques, because databases always think and that they know better than the operating system. Like they schedule, they manage memory, because they have more information than the operating system. And there is also hardware and co-designing software, so optimizing your software, knowing about the hardware, and sometimes even trying to create hardware, but well, that has not been very successful. Yeah, so, and it's about software architecture. So these are huge buildings of software, and there is not an optimal building, and there's also not an optimal architecture up front. There are always trade-offs. You have various desirable features of your new database system, but I mean, going all in on one feature may compromise other features that you, or other properties that you would want to have. So it's always a trade-off. How do you balance these? Writes versus reads, size versus computation, flexibility versus efficiency. Okay, so yeah, there is a rich academic and research tradition, and we have Turing Award winners who were database researchers, like well, God, but he didn't like systems. But Jim Gray and Michael Stonebreaker did, so they won two Turing Awards. Yeah. At CWI, we do database systems research, and I must honor here Martin Kersten, who sadly passed away already 3 years ago. He created the database research group here in Amsterdam at CWI, the first research group in database systems. And yeah, inspired also the philosophy of this group, which is a lot about not only writing papers, but actually writing code, and the joy of creating systems and learning from that. Not only about joy, but you can only really get insights if you actually try to implement something, then experiment with it and learn about its properties, which you cannot really always pre-compute from your design on paper. It will turn out in the end, in practice, how your system really behaves, and you will have to understand it as such. Okay, now past, present, and future, and starting with the past. So in databases, yeah, this group and the Netherlands, by extension, has influenced the field. Right, first using this whole phenomenon of column stores. Column stores are now quite standard. If you have an analytical database system, it's likely to be a column store, and that started here. It started with MongoDB. That was the system that Martin gave to me when I was a PhD student. He had 3 source code files, and he told me, well, make something out of this. And then, yeah, okay, I did. And now there is still actually a company called MongoDB Solutions that still develops this very, very first column store. And yeah, this was also inspired by big data started. Memories in computers started to become larger, but also relatively slower, because yeah, CPUs hit the gigahertz speeds, and then suddenly memory is quite far away, and you have cache misses, and then you try to optimize your memory access, and column stores are a good idea for that. And yeah, so up until that moment, the database systems that we knew at the moment, like we are talking now about 1994, okay, that was the first generation of relational systems. Oracle, Postgres were there. And these were transactional systems, so there was not really a category of analytical systems, and that kind of started with this stuff. Also, new applications started data mining, and there was a startup that we started here called Data Distilleries that was built on top of MongoDB, and that was the first startup I was involved in as a PhD student. And as I mentioned, MongoDB, the system, became open source, and there is still a company around this, led now by Niels Ness. And they are close by here in Science Park. But yeah, this got picked up. Among other things, among other people, we were invited by Hasso Plattner to give a talk about, okay, what are these column stores? So we went to Waldorf and we gave some talks. And then they built HANA as an early column store. But then Stonebreaker also got into column stores. He created a system called Vertica. And many more systems started to adopt the idea. Second thing that came out of Amsterdam is vectorized query processing. That is a different way of executing queries. MongoDB had a column at a time approach, and in vectorized query processing, we said, well, that's maybe not so efficient. We should actually do things in smaller chunks called vectors. And yeah, that model has also been adopted. The PhD student who worked most on that was Marcin Zukowski, and last year we gave him the Dijkstra Award for his impact on the field. He created also a startup company called Vectorwise. Vectorwise was built around, we had a new system. It was the first vectorized query engine. And it was acquired by a company called Actian, which was actually the company that owned Ingress. Ingress had been spun out of Computer Associates. It was a kind of weird plan. So then they wanted to take revenge on Larry Ellison. They wanted to reconquer the market, a completely unrealistic aim, of course, at that moment, because we're talking about 2005. Didn't work out. And then their plan B was, okay, let's conquer the analytical market. And then they did this deal with us. But yeah, the Ingress crew was not very successful commercially. But other systems were, like Dremel adopted the idea of column stores, and Drill, Impala was an early system. But now you have Databricks, SQL Server also adopted this. Oracle has something called Heatwave. ClickHouse, of course, is in Amsterdam, is also a columnar system. Snowflake. Yeah, so in the data format of Vectorwise, Fabian was complaining about encodings. So we also started that stuff. So that once you have columnar storage, because every column compresses relatively better than rows. And that is because everything in a column follows, well, the distribution that has to do with that column. If it's a last name or a first name, then you have only first names in this first name column. And because it's from a single distribution, the entropy is less. And because the entropy is less, you can compress it better than if you would mix all the values from a row with each other, because then your mixing distributions have more chaos. And then so you can kind of exploit this with encodings, like run length encoding, delta encoding, dictionary encoding. And this stuff that was in Vectorwise was adopted by Snowflake. Not maybe surprising, because Marcin Zukowski became the third co-founder of Snowflake. So CWI PhD graduate, founded record IPO company Snowflake. And Vectorwise fell by the wayside because Actian was not successful commercially. And what happened is that Databricks picked up the team. And that's the reason that Databricks has a large office in Amsterdam, because they started their Amsterdam office with the ex-Vectorwisers, without Marcin, who had founded Snowflake, which is their biggest competitor in the analytics market. And here they had this is already an old announcement that they would fund this office with 100 million in the next 5 years. Actually, this year, Databricks got this 15 billion. So that's not an IPO, but they did this on the Series K or something. I don't know. And they used that to pay out the RSUs of many of the many of Databricks who are now, I suppose, millionaires, who is also got a lot of that money. Probably 50% is the Dutch tax office and the American tax office, because this was a huge payout. And this 15 billion, let's say half of it probably went to various tax offices, unless people, of course, took evasive measures. Possibly, but I don't know. So this 100 million became even bigger, let's say, recently. And yeah, in the wake, no, okay, I don't actually know what I want to say. So it's the present here. Present in the group is DuckDB. So we are very much in the DuckDB era in our group right now. Yeah, what is DuckDB? I hope you know. So DuckDB is an analytical database system that is so-called embedded. So you can, just like Berkeley DB, you can link it to a program and it runs inside the same process as that program. But it was the first, yeah, you could also call it the SQLite for analytics. I think they sometimes call themselves that. But there was no analytical system that could do that. Initially, they started working on this because, and they is Hannes Mueijsen and Mark Raasveld. So Hannes is technically still my colleague in the database architectures group, but in practice, he is a Radboud professor 1 day a week, and the rest of his time, he is the CEO of DuckDB Labs, which is the spin-off company around DuckDB. And Mark Raasveld was Hannes's first PhD student and is now the CTO of DuckDB Labs. He reviews all PRs. He determines what goes in and what does not go into DuckDB. So why did they start on this? Because they saw that in data science, people were using pandas and they were not using database systems. And pandas kind of aspires to do things that are actually normally done by database systems, like filtering and joining and aggregating. And the question was, okay, why do data scientists hate databases so much? Well, there turned out to be good reasons why that was. And this group had always focused a lot of performance, but it's also, but the main reason is, I think, about usability. So DuckDB really focuses on making the database system pleasurable and easy to use. So for me, it was kind of an eye-opening thing that's also an area that you can do research in. Because time to solution is not only waiting for the answer to the query, but it's also figuring out which query, the correct query, how can you formulate the correct query. A system that helps you doing that quicker, yeah, can really become extremely popular. And DuckDB is now extremely popular and getting more and more popular every day. I think has been for for 5 years certainly the fastest growing database system in the world, and also the steepest riser in the DB engines ranking, if that means anything to you. Yeah, I'm not sure what I was. Yeah, currently, last in the news, I think, is the bid for from the DuckDB people to change the landscape in data lakes. So they launched something called Duck Lake. Duck Lake actually is not really something that you need to use DuckDB for, theoretically at least, because it's a standard and anybody could implement that standard. But currently, I think the only real practical implementation of it is in DuckDB. The idea is, yeah, this is Iceberg. Okay, that's the most popular data lake around currently. This is Duck Lake. Duck Lake is a more simple architecture. So the thing with Iceberg is that it has this whole hierarchy of files, Avro files. So we learned about Avro files. These are Avro files. Actually, this is a JSON file. The top one is a JSON file. In the middle, you have 2 layers of Avro files, and then at the bottom we have Parquet files. I dare show this slide thanks to Fabian's presentation, because now you know what these files are. This has become quite popular in the sense that, yeah, it allows you to have fleets of even 1 million Parquet files that represent one table. Sometimes, if you have really large applications, that will happen. And you can easily more easily manage them using these data lakes. And this whole file-based business is because people store these data lakes in the cloud in blob stores like S3, which like to store files. But yeah, in the end, Iceberg came out, and there's now a catalog war ongoing. Like the Iceberg people, they have this Polaris catalog, and Databricks has Unity catalog. And yeah, DuckDB says, well, you don't need all these files, you put everything in the catalog. Then you just have one metadata query that tells you which Parquet files you need to scan if you want to read the table. And it can also do the metadata filtering for you. So you have to read less footers, and things become much more simple. And you get nice properties of database because you now can do a transaction. Get transactionality in these metadata operations. Believe it or not, using a database system, such a good idea, also for metadata. Another thing that came with DuckDB is MotherDuck. MotherDuck is a second company because the core team of DuckDB, Hannes Mark, our CEO and CTO of DuckDB Labs, which is a relatively small team also across the road here. But MotherDuck is an American company that is also larger in amount of people. They have an office in Amsterdam, but also in the US, they have 3 offices in Seattle, San Francisco, and New York. And their mission is to bring the DuckDB to the cloud. So to run a cloud-based DuckDB service. And they raised a lot of money. So they raised in total now under 20 million. And yeah, they made something kind of cool. So you can go to app.motherduck.com. I know quite a bit about it because they gave me this t-shirt. Because I was on a sabbatical with the MotherDuck, and I still am there 1 day a week still. So I try to help them make that into a success. And the idea, what's maybe interesting about MotherDuck, maybe the one thing to remember is it has this hybrid query processing model where you have a DuckDB on your laptop and a DuckDB in the cloud. Because DuckDB is an embedded database system. That means that if you consider the JDBC client of DuckDB, what that means is that DuckDB is inside the JDBC client because it's the thing that you link to your application. And because all the clients that you might use to talk to a DuckDB already have a DuckDB in the library, we thought, okay, maybe you can use something useful with that local DuckDB that you now also have. You want the DuckDB in the cloud, yes, but you also have one on your laptop or in your web app. You can use it for caching and for post filtering, so MotherDuck can do interesting things with this dual execution, as they now call it. Okay, how are we on time? I will be short, but that's probably not a problem. Something about the future. So in this group, we do research. So we try to advance data systems into new directions. I will highlight 3. The first one is data formats. So we heard a long rant about what's not good about Parquet. Also, an interesting lead up to this slide here. So my now postdoc Azim has been working on a project called Fast Lanes. So what we think is that there's a lot of workloads now that use data that are actually AI workloads. So AI workloads are booming, and everybody tries to use AI for everything. And it's very important to keep those very expensive GPUs busy and not waste a lot of resources, either memory or compute on well, decompressing or parsing files. And Parquet is very GPU unfriendly, and it's the standard for analytical data. So actually a lot of analytical data is in Parquet. And a lot of that analytical data, or a lot of the data goes also into GPUs. And yeah, GPUs, yeah, if you want a GPU to decompress snappy, that's not going to be very efficient, because GPUs are highly parallel machines. They operate on with a very different computational model, these VARPs. So everything happens, 32 threads need to do exactly the same thing all the time in a GPU. So it's a very different programming model than a CPU. So if you want to decompress data, you also need to have a decompressor that can do 32 exactly the same things on different data at the same time. Snappy is not that, because it's very, it's a general purpose compression algorithm. So you will never get that data parallel. So the idea of fast lanes is to use so-called data parallel encodings and combine them, because if you just use one encoding, then like what Fabian said, sometimes that's not enough, and then you really need to, things really get smaller if you do snappy. But then if you do multiple of those encodings, then you get things smaller and you don't need to snappy anymore. So that is what Fastlane tries to do. And what we are now also trying to do is to learn smarter ways of storing data in fast lanes using AI. So that's still that's actually something that just started. Another thing, Daniel's in the room here, that we are doing is graph databases. SQL is SQL is a perverted standard. It's not really a standard. It's actually the ISO committee that makes SQL is completely bought by Larry. Larry, the guy who pays him. And in SQL, you don't even know what 1 divided by 3 should return. So that is actually that's a scandal. In a programming language like C or C++, that is defined, but in SQL it's not. And that is on purpose, is my theory, because that makes every SQL implementation incompatible with every other implementation. And under the guise of adopting something that is a standard, companies have en masse adopted something that is completely not a standard, and where customers are captives, and they know they will face very high migration costs if they ever would think of migrating from one SQL implementation to the other. Anyway, sorry, that's my rant on SQL. But there is SQL 2023. That is the latest version that got adopted. It's a very, very, very thick book, SQL now. It's actually, the way this is written is also, it's on purpose. But SQL 23 introduced a new feature, a property graph query, which is kind of interesting because it tries to make SQL databases do things that graph databases can do, like finding paths and pattern match in graph structures. You can, of course, store graphs in databases. A graph, G is V, E, okay, as we know, vertices and edges, V and E. So it's basically a V table and an E table. You can perfectly model a graph there. And that's what this extension does, because then you can say, oh, some tables that I already have, they store vertices, and other tables store edges. And the edges are basically foreign key kind of relations that point to the vertices, a source and a destination. That's what this does. It's basically a view that you can now put on top of tables that you have. And then if you do that, then there is some new syntax that looks like, if you would know Neo4j and Cypher, it's query language, it looks like that. And so we have been looking at this, and in the context of DuckDB, and Daniel has created something called DuckPGQ that adds this syntax. That's, by the way, also a problem. Adding syntax, SQL is a very syntax-driven, very syntax-heavy language. If you compare it to pandas, in pandas everything is a function. And you just have a function name and parentheses, and then with this you can extend it in many ways. But if you want to extend SQL, we always end up with new words like match and where and columns, and every new syntax extension of SQL adds more syntax, because the language is not really designed for being extensible. And also software engineering has not even figured out a way how you can make a parser extensible. So if you would have a base parser and you would have a runtime extension that would modify the syntax, you would have to kind of completely rewrite your YAC grammar or whatever, and then run it again. And then some completely different state machine would come out, but it's not something that you can do at runtime. You would have to completely recompile, and it's a monolith. It is one thing, you know, then you have something extra, but it's not like you can easily have extension modules to modify the syntax. That's actually also, and that's what Daniel is doing now. He's looking into ways of maybe something called pack parsing, and that can maybe help also this aspect of extensibility. Finally, you may have heard about vector search. I used the term vectorized query execution. That has nothing to do with vector search. Well, it has the word vector with it in common. But vector search, vector databases is the newest and the hottest class of databases that we now have. You know, there's also, I forgot to name them, but there is a Dutch company that is very, very popular in vector search. VV8, exactly. They're very distributed. The CEO is here, so there's some people are actually in Amsterdam. But yeah, vector databases. They are all over the place. They are all over the place because of AI and RAG. Do we know what RAG is?
It's augmented generation.
Yes, yes. So people enrich prompts with background knowledge, and they use vector search to find fuzzy matches in background databases. So this vector search, what you do is you have concepts in a database, and now you can index them using, with a high dimensional vector, a high dimensional, that's like an array of floating point numbers. And then you can do nearest neighbor search. If you want something, I'm looking for Mokum, then presumably this word Mokum will produce a feature vector that's very close to the feature vector of Amsterdam, because the two concepts are very close to each other. That's the idea of vector search. And there are lots of different approaches. The most popular one is this one, HNSW. This is a kind of a graph-based HNSW, hierarchical network of small worlds or something like this. So it's kind of a graph index where, because you don't want to go through the complete database and compute all the distance between your query vector and the whole database. So what this graph does is you kind of hop selectively through, and hopefully to the most close by vectors. You don't have to look at them all. That is an ANN approach. ANN means approximate nearest neighbor search, because they hope that you find the closest ones, but they haven't looked at all of them, of course. But we have come up with something new. It's called PDX. It's the idea is not to use a graph or an index, because problem with indexes is that you have to maintain them, okay, and that is expensive. So, and sometimes when you delete, then you have to vacuum them, you know, so it's also not. So, it's a pain, and actually creating these HNSW indexes will take hours, even on not so big databases. So you don't want that. So we want something more simple. The alternative is basically partitioning. IVF, it's called. This is a partitioning-friendly layout, and what it actually does, it uses the idea of columnar storage, but for vectors, because most implementation, like PG vector, the very Postgres implementation of a vector, you basically create a large object, which is an array with all the floats. These arrays are huge, because we are talking about 1024 dimensional things. So that is, so one value is 4 kilobytes, at least. So these are really, really big things that will make your table very heavy as well. But they are stored typically as one record. So that's horizontal storage. It's a row, effectively, a row of floating points. But you could also do the other thing, column of floating points. Then you would separate them out, and you can maybe look at only part of the columns, and then maybe prune a lot and not look at all the data. So that is what PDX does. And so we think that this will significantly lower the cost for ingesting vectors. And it's very fast as well, because it's very SIMD friendly. SIMD is single instruction, multiple data instructions that you have, like Neon instruction, AVX 512 instructions in CPUs. So that's going down here, and we also think that that's interesting. So you can check this out in our GitHub CWI DA, PDX, and fast lanes was CWI DA fast lanes. These are things that we are. That's not the only things we're doing, but these were three things that you can actually download and toy with already with code right now. But yeah, work in our group is not only me. I'm talking, of course, but it's really teamwork. And I've like on the top row, you see the current group. For instance, yeah, Paul, who I should really thank a lot for organizing. Let's give Paul a hand of applause. PhD student, not the youngest, but he tried to make a bar chart, like strings in databases, more efficient. So a very basic topic, but most of the data that we have is strings, and most academic papers are about integers because strings are difficult. So yeah, but yeah, lots of volume is. So this is in the top row are the PhD students. Marlon is recently joined as a tenure tracker. Azim is now he's in the back. He's the fast lanes person. He's now a postdoc. But yeah, many of all those people all have been at CWI. They are now the core kind of group of WDB Labs. They were in the group, and this group of people, Marcin, but also others, they were in the Vectorwise team. They are now, most of them are at Databricks Amsterdam. And these are people who are, Niels is currently leading the MongoDB solutions company. Martin Kersten, he died 3 years ago. He was the founder of our group originally. So I would not have been able to do the things I'm talking about without all these talented people. Also, people at Databricks who I have advised on things like the Photon engine and Delta Lake, and the people at MongoDB, who are some of them also now in the room. So it's great. It's also it's about creating the technology, but it's also about creating a group of people, like a community with skills, and that's also why I like the initiative to have this Amsterdam DB meetup, because being a strong community is great and will also help the ecosystem thrive. And it's also a lot of fun. So thank you for your attention. Questions?
Why is that you talk about vector DBs in the context of regs, and because we had them for quite some time for recommender systems, because nearest neighbors is a very important query for highly dimensional vectors. So was there already a research before that?
Yes, I mean, I was like in our group, Arjen de Vries, he's now a professor in Nijmegen. He was at CWI until 15 years ago, but at the start of this millennium, he worked on vector search. We were then doing multimedia databases, he created an algorithm called Boncz, branch and bound on dimensional data or something like that. So yeah, the topic is older. At that moment, actually, if you really do, it didn't work so well, because doing vector search on the raw pixels, which what we were doing then, it's much less effective as doing vector search on an embedding created from a picture, because the embedding has much more semantic kind of logic in it, and it actually makes much more sense. We work at, like, some of the queries used could work. You would, if you had a tiger, then you would find other tigers, because you would have this. But it didn't really work until that moment, and it hit it really big in the ML wave, and certainly with RAG now. Everybody must have a vector DB already yesterday. So that's why this whole field is now so big. But it was older. Yeah.